Hello there, and welcome to the most unexpectedly soothing corner of science. Tonight, we're diving into a world so small, so ancient, and so quietly that it exists essential all around us without fan recognition. We're exploring fair or the gentle realm of bacteria, those microscopic companions that have been shaping our planet for billions of years, in ways both profound and beautifully simple. Now, before you think this sounds anything but relaxing, let me invite you to see bacteria through a different lens tonight. These aren't the villains of hand sanitizer commercials or the monsters hiding in your kitchen sponge. Instead, we're going to discover the bacteria that paint auroras in petri dishes, the ones that have been gardening for millions of years, and the ancient communities that work together in harmony so perfect it would make any meditation teacher weep with joy. If you find yourself drifting towards sleep as we wander through these microscopic marvels, that's exactly where you're meant to be. Feel free to like and subscribe if you enjoy these gentle journeys into science, or simply let your thoughts float along with the quiet wonders we'll uncover together. But for now, all you need to do is settle in, let your breathing slow, and allow yourself to be amazed by the tiny architects of our world. Let's begin our peaceful exploration. Some bacteria glow like living stars scattered across the earth. In the depths of our oceans, certain bacteria possess the remarkable ability to create their own light through a process called bioluminescence. These gentle creatures, with names like Vibrio harveyi and Photobacterium, carry within their microscopic bodies the same magic that makes fireflies twinkle on summer evenings. The light they produce is soft, ethereal, and surprisingly efficient. Unlike the harsh glare of artificial bulbs, bacterial bioluminescence creates a cool blue-green glow that seems to pulse with the rhythm of life itself. When these bacteria gather in large numbers, they can turn entire stretches of ocean into liquid starlight, waves that sparkle and dance with every movement of the water. What makes this phenomenon even more enchanting is the reason behind it. These bacteria don't glow to show off or to frighten predators. Instead, they use their light as a gentle form of communication, a way to signal to their neighbors and coordinate their activities. It's as if they're having quiet conversations in a language made entirely of light, passing messages through the darkness with the subtlety of distant stars. Some of these luminous bacteria have formed partnerships with larger creatures, living peacefully inside fish and squid, providing them with built-in lanterns in exchange for a safe home. The Hawaiian bobtail squid, for instance, carries these glowing passengers in a special organ, using their light to mask its shadow as it hunts at night. It's a relationship built on mutual benefit and trust, a microscopic example of cooperation that has endured for millions of years. Bacteria have been gardening longer than any civilization on Earth. Long before humans discovered agriculture, bacteria were already master farmers, cultivating their environment with a patience and skill that puts our grandest gardens to shame. These microscopic gardeners don't use tools or machinery, but they possess something far more elegant, an intricate understanding of chemistry that allows them to transform the world around them one molecule at a time. In the soil beneath our feet, bacteria work tirelessly to break down fallen leaves, dead animals, and organic waste, converting them into nutrients that plants can absorb. They're the invisible recyclers of our world, ensuring that nothing is ever truly wasted, that every ending becomes a new beginning for something else. This process happens so quietly, so efficiently, that we rarely think about the countless bacterial communities laboring beneath every step we take. Some bacteria specialize in nitrogen fixation, taking the abundant nitrogen gas from our atmosphere and transforming it into forms that plants can use to grow. Without these bacterial farmers, most plant life as we know it simply couldn't exist. They've been performing this essential service for billions of years, asking for nothing in return except a small space in the soil and the simple chemistry of their surroundings. Other bacterial gardeners focus on breaking down complex organic compounds, working like microscopic composters to turn yesterday's waste into tomorrow's fertility. They operate in communities with different species handling different aspects of the decomposition process, each playing their part in the gentle cycle of renewal that keeps our planet green and growing. These bacterial gardens extend far beyond soil. In the depths of the ocean, bacteria tend to underwater forests of chemicals, creating entire ecosystems around volcanic vents where no sunlight can reach. They harvest energy from the Earth's own heat and chemistry, supporting communities of creatures that exist in what would otherwise be a lifeless void. Ancient bacteria taught the Earth how to breathe. Billions of years ago, when our planet was young and the atmosphere contained virtually no oxygen, ancient bacteria called cyanobacteria began one of the most important experiments in the history of life. They learned to harness the energy of sunlight in a new way, using it to split water molecules and release oxygen as a byproduct. This process, which we now call photosynthesis, started slowly and quietly. For millions of years, these bacterial pioneers worked in the shallow seas, gradually releasing tiny amounts of oxygen into an atmosphere that had never known it before. The change was so gradual, so gentle, that it took nearly 1 billion years for oxygen levels to rise significantly. As these ancient bacteria continued their patient work, they began to transform not just the atmosphere, but the entire character of life on Earth. The oxygen they produced eventually allowed for the evolution of more complex organisms, creatures that could use oxygen to power their own cellular processes more efficiently than ever before. What's remarkable is that these cyanobacteria didn't set out to change the world. They were simply living their lives, using the resources available to them, following the gentle chemical processes that sustained them. Yet their quiet persistence over geological timescales literally made it possible for every oxygen-breathing creature that would ever exist, including us. Even today, billions of years later, cyanobacteria continue their ancient work. They float in our oceans, drift in our lakes, and form delicate films on rocks and soil around the world. Every breath you take contains oxygen that may have been produced by these microscopic descendants of the Earth's first atmospheric engineers. Some bacteria create underground networks more complex than any internet. Beneath the surface of our world, bacteria have constructed communication networks that span vast distances, connecting separate communities through intricate webs of chemical signals and shared resources. These networks, invisible to our eyes, represent some of the most sophisticated examples of cooperation and coordination in the natural world. The bacteria in these networks don't just live in isolation, competing for resources. Instead, they've learned to share information about food availability, environmental changes, and potential threats through when one bacterial complex system of chemical messaging, a new source of nutrients community discovers, it can signal this information to distant relatives, allowing them to benefit from the discovery. Some of these underground bacterial networks can extend for miles, creating vast interconnected communities that function almost like a single, distributed organism. Individual bacteria within the network specialize in different tasks, some focusing on nutrient processing, others on waste management, still others on communication and coordination. The sophistication of these bacterial networks is staggering. They can respond to environmental changes faster than many larger organisms, adapting their behavior and resource allocation in real time as conditions shift around them. They maintain redundant pathways for critical functions, ensuring that the network remains stable even if individual communities are damaged or destroyed. What's perhaps most beautiful about these networks is their resilience and cooperation. Rather than viewing other bacteria as competitors, the members of these networks have learned that their survival depends on the health and success of the whole community. They share resources during times of scarcity, support struggling members, and work together to overcome challenges that no individual bacterium could face alone. Bacteria have mastered the art of living in impossible places. While we humans require a narrow range of temperature, pressure, and chemical conditions to survive, bacteria have learned to thrive in environments that would instantly kill almost any other form of life. These extremophile bacteria, as scientists the boundaries of what we thought call them, have pushed what's possible for living creatures. Some bacteria live happily in water so hot it would boil away our skin, thriving in the scalding pools of geysers and the superheated water around underwater volcanic vents. Others prefer the opposite extreme, remaining active in ice so cold that most chemical reactions slow to a crawl. They've found ways to keep their cellular processes running smoothly, even when their surroundings drop far below the freezing point of water. There are bacteria that live in acid, so concentrated it would dissolve metal, and others that flourish in alkaline conditions that would burn through organic tissue. Some have learned to extract energy from environments with no oxygen at all, while others survive in the presence of radiation levels that would be lethal to virtually any other organism. Perhaps most remarkably, some bacteria can enter a state of suspended animation when conditions become too harsh, essentially pausing their lives until better times return. They can remain in this dormant state for thousands, even millions of years, waiting with infinite patience for the environment to become hospitable again. These extremophile bacteria aren't just surviving in impossible places, they're thriving there. They've turned the Earth's most hostile environments into thriving communities, proving that life is far more adaptable and resilient than we ever imagined. Their existence expands our understanding of where life might be possible, both on our own planet and potentially on others. Bacteria work together in cities more organized than our own. When we think of bacterial life, we often imagine individual microorganisms floating alone in liquid or scattered randomly across surfaces. But the reality is far more sophisticated and beautiful. Many bacteria live in highly organized communities called biofilms, structures so complex and well coordinated that they function like microscopic cities. These bacterial cities begin when a few pioneer bacteria attach to a surface and start producing a sticky matrix of proteins and sugars. This matrix acts like the foundation of their city, providing structure and protection for the growing community. As more bacteria join the settlement, they add their own contributions to the matrix, gradually building up layers of living architecture. Within these biofilm cities, Different bacteria take much on specialized roles, like professions in human society. Some bacteria focus on producing the structural materials that hold the community together. Others specialize in nutrient processing, breaking down food sources, and distributing the products throughout the city. Still others serve as waste management specialists, dealing with the byproducts of community life. The organization within these bacterial cities is remarkably sophisticated. The bacteria create channels and networks that distribute nutrients and oxygen throughout the community, ensuring that even bacteria in the deepest layers receive what they need to survive. They establish gradients of different chemicals, creating microenvironments within the city that are perfectly suited to different bacterial populations. Communication flows through these cities in the form of chemical signals, allowing bacteria to coordinate their activities and respond to changes in their environment. When food becomes scarce, the community can shift its behavior collectively, with some bacteria entering dormant states while others increase their foraging activities. These bacterial cities can grow to enormous sizes relative to their inhabitants, sometimes forming structures visible to the naked eye. They can be found everywhere, from the rocks in mountain streams to the surfaces of medical implants, from the hulls of ships to the inside of water pipes. Each one represents a triumph of cooperation and organization that has been perfected over billions of years of evolution. Some bacteria have learned to eat electricity like we eat food. In the depths of muddy lake bottoms and ocean sediments, remarkable bacteria have discovered how to survive on pure electrical energy. These electroactive microorganisms, with names like Geobacter and Shewanella, don't need sunlight or organic compounds to sustain themselves. Instead, they've mastered the art of consuming electrons directly from their environment. These electrical eaters work by extending tiny biological wires called pili from their cell surfaces. These microscopic cables can stretch for distances that are enormous by bacterial standards, connecting them to sources of electrical current in rocks, sediments, or even man-made structures. Through these connections, they draw in the electrons they need to power their cellular processes, much like we might plug into a wall socket. What makes this even more fascinating is that these bacteria don't just consume electricity in isolation. They often work together in chains and networks, passing electrons from one bacterium to another, like a microscopic electrical grid. Some bacteria generate excess electrons and share them with neighbors who need them, creating a living circuit that spans entire sediment layers. Scientists have discovered that these electroactive bacteria can even help clean up pollution. They can consume toxic metals and break down harmful chemicals by using them as sources of electrons. In essence, they're turning environmental contamination into their own personal power source, slowly purifying their surroundings while sustaining themselves. The discovery of these electricity-eating bacteria has opened up entirely new possibilities for biotechnology. Researchers are exploring ways to use them in living batteries, in systems that can generate clean energy from waste, and in devices that could help restore damaged environments. These tiny electrical engineers are showing us new ways to think about the relationship between life and energy. Bacteria create their own weather systems in miniature worlds. Within the microscopic realm that bacteria inhabit, complex weather patterns emerge that mirror the grand atmospheric systems of our planet. Individual bacterial communities generate their own chemical winds, pressure systems, and seasonal cycles that govern life in their tiny domains. When bacteria consume nutrients, they create chemical gradients that flow through their environment like invisible currents. These gradients carry dissolved minerals, gases, and signaling molecules, distributing resources and information throughout bacterial territories, much like atmospheric circulation distributes heat and moisture across continents. Some bacteria actively modify their local environment to create more favorable conditions, much like how forests can influence regional rainfall patterns. They release specific chemicals that can alter the acidity, temperature, or oxygen levels in their immediate surroundings, engineering their own microscopic climate zones. Temperature fluctuations in bacterial environments can be surprisingly dramatic. As bacterial communities metabolize and generate heat, they create warm spots that attract certain species while repelling others. These thermal patterns can shift and change over time, creating seasonal-like cycles that influence which bacteria thrive and which ones enter dormant states. Chemical storms can sweep through bacterial communities when environmental conditions change rapidly. A suddenness of nutrients might create a feeding frenzy that alters the entire chemical landscape, while the depletion of essential resources can trigger community-wide adaptations that ripple through the bacterial ecosystem like weather fronts moving across a continent. These microscopic weather systems are remarkably stable and predictable. Bacterial communities often establish equilibrium patterns that can persist for long periods, with regular cycles of activity and rest that mirror the dependable rhythms of earthly seasons. In their tiny worlds, bacteria experience the same kinds of environmental cycles that govern life at every scale. Ancient bacteria invented recycling billions of years before humans existed. Long before the concept of waste management entered consciousness, bacteria had already perfected the art of turning every ending into a new beginning. These microscopic recyclers operate with an efficiency that makes our modern recycling efforts look crude by comparison. Every carbon atom in your body has likely passed through countless Ling systems bacterial recycle over the eons. These ancient processors break down complex organic molecules into their component parts, then carefully reassemble them into new forms that other organisms can use. Nothing is ever truly discarded in the bacterial world, only transformed and repurposed. Different bacterial species specialize in different aspects of the recycling process. Some focus on breaking down proteins into amino acids, others work on decomposing carbohydrates into simple sugars, and still others handle the processing of fats and other lipids. Together, they form recycling chains that can completely dismantle and rebuild virtually any organic compound. The bacterial recycling process operates on multiple timescales simultaneously. Some recycling happens within minutes as bacteria quickly process simple nutrients. Other cycles can take months or years as bacteria slowly work through complex materials like wood or bone. The most patient bacterial recyclers work on geological time scales, gradually breaking down rocks and minerals over millions of years. These recycling networks extend throughout every ecosystem on Earth. In forests, bacterial recyclers work in the soil to process fallen leaves and dead animals. In oceans, they handle the constant rain of organic matter that falls from the surface waters. Even in the most extreme environments, bacterial recyclers continue their quiet work, ensuring that the cycle of life never stops. The efficiency of bacterial recycling is so complete that if these processes were to stop, life on Earth would quickly grind to a halt. Nutrients would become locked up in dead organic matter, unavailable to living organisms. The bacterial recyclers are the invisible foundation that makes all other life possible, working tirelessly to keep the elements of life in constant circulation. Some bacteria can survive being launched into space and still remain alive. The resilience of certain bacterial species extends far beyond anything we might consider reasonable for living organisms. These hardy microorganisms, known as extremophiles, have demonstrated an ability to survive conditions that would instantly destroy most other forms of life, including the harsh vacuum and radiation of outer space. When scientists have accidentally sent bacteria into space on spacecraft or deliberately exposed them to space-like conditions in laboratories, some species have not just survived but remained capable of reproducing once returned to more hospitable environments. They can withstand the complete absence of air, temperatures that fluctuate between hundreds of degrees above and below zero, and radiation levels that would be immediately lethal to humans. These space-surviving bacteria achieve their remarkable resilience through several elegant strategies. Some can form protective spores that essentially pause their life processes until conditions improve. Others produce special proteins that repair cellular damage as quickly as it occurs. Still others can actually feed on radiation, turning this deadly force into a source of energy. The discovery of space-surviving bacteria has profound implications for our understanding of how life might spread throughout the universe. It suggests that microorganisms could potentially travel between planets on asteroids or comets, seeding new worlds with life. This possibility, known as panspermia, means that life might be far more widespread in the cosmos than we previously imagined. These hardy bacteria also provide insights into the possible origins of life on Earth. If bacteria can survive the journey between worlds, then perhaps life on our planet began with microscopic travelers from elsewhere in the solar system. The bacteria living quietly in soil samples today might be the descendants of ancient space voyagers who arrived billions of years ago. The ability of bacteria to survive in space also offers hope for future human space exploration. Understanding how these microorganisms protect themselves from cosmic hazards could help us develop better protection systems for human astronauts on long journeys to other planets. Bacteria have been making medicine longer than humans have existed. Throughout the natural world, bacteria have been producing compounds with remarkable healing properties for billions of years. These microscopic pharmacists create complex chemicals that can fight infections, reduce inflammation, and even help repair damaged tissues. Many of the most important medicines in human history were originally discovered in bacterial communities. The antibiotics that have revolutionized human medicine are largely products of bacterial warfare. In their competitive microscopic world, bacteria have evolved sophisticated chemical weapons to defend their territory from rivals. Penicillin, streptomycin, and countless other life-saving drugs are essentially bacterial defense systems that we've learned to harness for our own medical needs. But bacteria don't just make medicines for fighting other microorganisms. Some produce compounds that can help larger organisms heal from injuries or resist diseases. Scientists have discovered bacterial communities that create natural painkillers, anti-inflammatory agents, and even chemicals that can help stimulate tissue regeneration. The pharmaceutical potential of bacteria extends far beyond what we've already discovered. In every environment scientists study, from deep ocean trenches to high mountain peaks, they find bacterial communities producing novel compounds with unexpected medical properties. Each new bacterial species represents a potential pharmacy of unexplored medicines. Some bacteria even seem to understand the concept of personalized medicine. They can adjust the types and concentrations of compounds they produce based on the specific conditions in their environment. When faced with different types of threats or challenges, bacterial communities can modify their chemical output to address the particular problems they encounter. The relationship between bacteria and medicine is so fundamental that our own bodies depend on bacterial medicine production. The beneficial bacteria living in our digestive systems produce vitamins, help regulate our immune systems, and even manufacture mood-regulating chemicals that influence our mental health. We are walking ecosystems supported by microscopic doctors who work around the clock to keep us healthy. Bacteria have been composing symphonies in frequencies we're only beginning to hear. In the quiet spaces between soil particles and within the flowing currents of streams, bacterial communities create acoustic landscapes that exist far below the threshold of human perception. These microscopic musicians don't use instruments or vocal cords, but rather the subtle vibrations of their cellular processes, the rhythmic pulsing of their metabolic cycles, and the gentle resonance of their chemical communications. When bacteria move, they create tiny pressure waves that ripple through their liquid environments. When they feed, their cellular machinery generates microscopic vibrations that propagate outward like the softest whispers. When they reproduce, the process of cell division creates acoustic signatures that other bacteria can detect and respond to, forming the basis of a sound-based communication system that predates any form of music humans have ever conceived. Different bacterial species contribute different notes to these microscopic orchestras. Some produce steady, droning tones through their consistent metabolic rhythms. Others add staccato bursts of activity that punctuate the bacterial soundscape like percussion instruments. Still others create sweeping crescendos as their populations grow and expand, their collective acoustic output swelling like a chorus reaching toward a climactic moment. These bacterial symphonies serve practical purposes in their microscopic world. The acoustic patterns help bacteria coordinate their activities, signaling when it's time to move, when resources are available, or when environmental conditions are changing. They use sound as a way to maintain the spacing and organization of their communities, ensuring that each member occupies its optimal position within the larger acoustic ensemble. Scientists studying these phenomena have discovered that bacterial communities can actually synchronize their acoustic outputs, creating coordinated performances where millions of individual bacteria contribute to complex, harmonious patterns. The precision of this synchronization rivals that of the finest human orchestras, yet it emerges spontaneously from the simple interactions between countless microscopic performers. Some bacteria create living clocks more accurate than our finest timepieces. Within the cellular machinery of certain bacterial species, biological chronometers tick with a precision that puts even atomic clocks to shame. These microscopic timekeepers don't rely on pendulums or quartz crystals, but rather on the intricate chemical oscillations that govern their internal processes. The bacterial sense of time operates on multiple scales simultaneously. Some bacterial clocks measure the passage of seconds and minutes, tracking the optimal timing for feeding, reproduction, and movement. Others keep track of longer cycles, following the rhythm of days and seasons, even in environments where no external cues about time are available. What makes bacterial timekeeping so remarkable is its reliability across vastly different conditions. Whether subjected to temperature extremes, pressure changes, or chemical fluctuations that would destroy human-made clocks, bacterial chronometers continue to tick with unwavering accuracy. They maintain their temporal precision through elegant molecular mechanisms that automatically compensate for environmental variations. These biological clocks aren't just internal curiosities. Bacteria use their temporal awareness to coordinate complex community behaviors, timing their activities to maximize efficiency and minimize conflicts with neighboring microorganisms. Some bacterial processes can only occur at specific times in their cellular cycles, and the precision of bacterial timekeeping ensures that these critical events happen exactly when they should. The study of bacterial chronometry has revealed that time for these microorganisms is not a simple linear progression, but rather a complex web of interlocking cycles and rhythms. Different cellular processes operate on different temporal scales, from the rapid-fire chemical reactions that occur thousands of times per second to the slow seasonal adaptations that unfold over months or years. Certain bacteria have mastered the art of chemical telepathy. In the invisible realm where bacteria live, thoughts take the form of molecules, and communication happens through the precise release and detection of chemical signals. These microscopic telepaths can share information across distances that are vast by bacterial standards, passing complex messages through networks of chemical intermediaries. The chemical vocabulary that bacteria use for this molecular telepathy is surprisingly rich and nuanced. Different chemical compounds convey different types of information, from simple alerts about food availability to complex instructions for coordinating group behaviors. Some bacterial messages are like whispered secrets, detectable only by closely related species, while others are broadcast announcements that can be understood by diverse microbial communities. What makes bacterial telepathy even more fascinating is its speed and accuracy. Chemical messages can travel through bacterial communities faster than electrical signals move through computer networks. The receiving bacteria can decode these molecular transmissions with remarkable precision, extracting detailed information from chemical concentrations that vary by just a few molecules per billion. Some bacteria have evolved the ability to amplify and relay chemical messages, creating communication networks that can span enormous distances relative to their microscopic scale. A chemical signal that originates in one corner of a bacterial colony can be passed from cell to cell, potentially reaching bacteria that are millions of body lengths away from the original sender. The sophistication of bacterial chemical telepathy extends to the ability to encrypt and decode messages. Some species use complex chemical signatures that can only be properly interpreted by bacteria with the correct molecular keys. This allows them to maintain private communication channels even in crowded microbial environments, where many different species are simultaneously broadcasting their own chemical messages. Bacteria have been practicing architecture longer than any human civilization. The structures that bacteria build are marvels of microscopic engineering, created without blueprints or tools, yet exhibiting a sophistication that rivals the greatest achievements of human architects. These bacterial builders work with materials they manufacture themselves, constructing edifices that can last for thousands of years while remaining flexible enough to adapt to changing conditions. The architectural repertoire of bacteria includes towering spires that can reach heights of several millimeters, enormous by bacterial standards. These structures, built from carefully secreted proteins and polysaccharides, serve as both homes and fortresses, protecting bacterial communities from environmental hazards while providing optimal conditions for growth and reproduction. Some bacterial architects specialize in creating underground cities, vast networks of tunnels and chambers that extend deep into soil and sediment. These subterranean structures are engineering marvels with carefully designed ventilation systems that ensure proper circulation of nutrients and waste products throughout the entire complex. The bacterial builders incorporate drainage systems, structural supports, and even emergency escape routes into their underground metropolises. Other bacteria focus on surface construction, building elaborate towers and domes that rise above their surroundings like microscopic skyscrapers. These aerial structures are often equipped with sophisticated sensing systems that allow the bacterial inhabitants to monitor environmental conditions and respond quickly to changes in their surroundings. The construction techniques employed by bacterial architects are remarkably advanced. They assemble materials that automatically self-organize themselves into the desired shapes and structures. They incorporate feedback systems that allow buildings to repair themselves when damaged and to grow or shrink as the needs of the community change. Perhaps most impressively, bacterial architecture is inherently sustainable. These microscopic builders create structures that are completely biodegradable, designed to be recycled and repurposed when they're no longer needed. Nothing is wasted in bacterial construction projects, and every building eventually becomes the raw material for future architectural endeavors. Some bacteria can paint with pigments more vibrant than any artist's palette. In the microscopic world, color serves purposes far beyond mere decoration. Bacterial painters create stunning displays of hue and saturation, producing pigments that can shift and change in response to environmental conditions, creating living artworks that evolve continuously over time. These bacterial artists don't use brushes or canvases. Instead, they paint with their own cellular machinery, secreting complex organic compounds that interact with light in precisely controlled ways. Some bacterial pigments are so intense that they can be seen with the naked eye when bacterial communities reach sufficient size, creating brilliant patches of color that seem to glow from within. The color palette available to bacterial painters is vast and varied. Some species specialize in deep purples and rich blues, creating pigments that absorb specific wavelengths of light with remarkable efficiency. Others work with brilliant reds and oranges, producing compounds that seem to capture and concentrate the warmth of sunlight itself. Still others paint in subtle earth tones, creating pigments that blend harmoniously with their natural surroundings. The purposes behind bacterial painting extend far beyond aesthetics. Many bacterial pigments serve as sophisticated light harvesting systems, allowing these microorganisms to capture and utilize solar energy with an efficiency that surpasses the best human-made solar panels. Other pigments function as protective agents, shielding bacterial communities from harmful radiation or chemical toxins. Some bacterial artists create dynamic paintings that change throughout the day or season. Their pigments can shift from one color to another in response to temperature, light levels, or chemical signals, creating living murals that tell the story of environmental conditions over time. These chromatic displays serve as both art and information, beautiful expressions of the bacterial community's adaptation to their changing world. The techniques used by bacterial painters are remarkably sophisticated. Some species layer different pigments to create complex color interactions, while others mix pigments in precise ratios to achieve exactly the desired shade. Many bacterial artists can adjust the intensity and distribution of their pigments in real time, fine-tuning their colorful displays to match the immediate needs of their community. Bacteria have been writing the world's longest-running diary in languages made of chemistry. For billions of years, bacterial communities have been recording the history of our planet in chemical signatures that persist long after the microorganisms themselves have passed away. These molecular records contain detailed information about ancient climates, atmospheric compositions, and environmental changes that stretch back to the very beginning of life on Earth. The bacterial diary is written in multiple chemical languages simultaneously. Some bacteria record their experiences in the isotopic ratios of the elements they incorporate into their cellular structures. Others leave behind distinctive molecular fossils, complex, organic compounds that can only be produced by specific types of bacterial metabolism. Still, others write their stories in the minerals they precipitate, creating geological signatures that preserve information about ancient bacterial communities. Reading the bacterial diary requires sophisticated analytical techniques, but the stories it contains are incredibly detailed and accurate. Scientists can determine not just when ancient bacteria lived, but also what they ate, how they reproduced, and what environmental challenges they faced. The chemical records left by bacterial communities provide insights into past climate conditions that are more precise than any other source of paleoenvironmental data. The bacterial diary is continuously being updated as new entries are added by contemporary microbial communities. Every day, bacteria around the world are writing new chapters in this ongoing chemical chronicle, recording current environmental conditions in molecular form for future generations of scientists to discover and interpret. What makes the bacterial diary particularly valuable is its global scope and temporal coverage. Bacterial records can be found in every environment on Earth, from the deepest ocean sediments to the highest mountain peaks. These chemical archives span the entire history of life on our planet, providing an unbroken record of biological and environmental change that extends back over 3 billion years. The preservation of bacterial chemical signatures is remarkably robust. Unlike written records or artifacts that can be destroyed by fire, flood, or decay, bacterial molecular fossils can survive for geological ages, remaining readable even after being subjected to extreme pressure, temperature, and chemical alteration. This makes the bacterial diary one of the most durable forms of historical record ever created. Ancient bacteria invented solar power billions of years before humans discovered electricity. The photosynthetic systems developed by early bacterial communities represent some of the most elegant and efficient energy conversion technologies ever devised. These microscopic solar engineers learned to capture sunlight and transform it into usable chemical energy with a precision and effectiveness that modern solar panels can only aspire to match. The bacterial approach to solar energy harvesting is fundamentally different from human technology. Rather than using silicon wafers and electrical circuits, Bacteria employ complex organic molecules that can absorb specific wavelengths of light and channel that energy through carefully orchestrated chemical pathways. These biological solar panels are self-repairing, self-optimizing, and incredibly efficient at extracting useful energy from even dim or filtered sunlight. Different bacterial species have specialized in harvesting different portions of the solar spectrum. Some focus on the high-energy blue and ultraviolet wavelengths, while others have adapted to utilize the longer, lower-energy red and infrared portions of sunlight. This specialization allows bacterial communities to collectively harvest nearly the entire spectrum of solar radiation, maximizing the energy available to their ecosystems. The efficiency of bacterial solar power systems is truly remarkable. While the best human-made solar panels convert about 20% of incident sunlight into usable energy, bacterial photosynthetic systems regularly achieve conversion efficiencies of over 90%. This extraordinary performance is achieved through quantum mechanical processes that allow bacterial solar collectors to transfer energy with almost loss to heat or no other wasteful pathways. Bacterial solar power systems are also incredibly adaptable. They can adjust their sensitivity and spectral response based on changing light conditions, optimizing their performance throughout the day and across seasons. When light levels are low, bacterial solar collectors can increase their sensitivity to capture more of the available photons. When light is abundant, they can adjust their systems to avoid damage from excessive energy input. The longevity of bacterial solar power is equally impressive. While human solar panels degrade over time and typically need replacement after a few decades, bacterial photosynthetic systems can operate continuously for thousands of years without significant loss of performance. The self-repairing nature of biological systems means that bacterial solar collectors can maintain their efficiency indefinitely, constantly renewing and upgrading their energy harvesting capabilities. Some bacteria have mastered time travel by preserving perfect moments indefinitely. Through the remarkable process of sporulation, certain bacterial species can effectively pause their existence, creating time capsules that preserve their genetic information and cellular machinery in a state of suspended animation that can last for millions of years. These bacterial time travelers don't need complex machinery or exotic physics, just the elegant biological mechanisms they've refined over eons of evolution. When environmental conditions become unfavorable, these prescient bacteria begin the intricate process of creating spores, essentially packaging their most essential components into nearly indestructible protective shells. The spore formation process is like watching a master craftsman at work as the bacterium carefully selects which proteins, genetic material, and cellular components to preserve while systematically dismantling everything else. The protective shells that bacteria create for their time travel adventures are marvels of biological engineering. These microscopic capsules are resistant to heat that would melt metal, cold that would freeze most chemical reactions solid, radiation that would destroy electronic equipment, and chemical conditions that would dissolve ordinary biological materials. Some bacterial spores have survived being boiled, frozen, irradiated, and exposed to the vacuum of space, emerging unharmed when favorable conditions return. The patience of bacterial time travelers is truly extraordinary. While humans measure significant time periods in decades or centuries, bacterial spores can wait for millions of years without any sign of deterioration. Scientists have successfully revived bacterial spores from ancient salt crystals, amber deposits, and ice cores that date back to prehistoric eras, proving that these microscopic time capsules can preserve life across geological ages. When conditions finally become suitable again, the bacterial time travelers begin their return journey to active life. The spore germination process is like watching a flower bloom in extreme slow shell gradually motion, as the protective dissolves and the preserved cellular machinery slowly comes back to life. Within hours, a spore that may have been dormant for millennia can transform back into a fully active, reproducing bacterium, ready to continue the story that was paused so long ago. The implications of bacterial time travel extend far beyond individual survival. These patient microorganisms serve as living libraries, preserving genetic information and evolutionary adaptations across vast spans of time. They represent a form of biological backup system, ensuring that valuable genetic innovations developed in ancient environments can be recovered and reused when similar conditions arise in the future. Bacteria create invisible highways that span entire continents. Beneath our feet and beyond our sight, bacterial communities have constructed transportation networks that dwarf any human infrastructure project. These microscopic highways carry not vehicles or people, but chemical signals, nutrients, and even genetic information across distances that are practically infinite from a bacterial perspective. The construction of bacterial highways begins with the secretion of specialized guidance molecules that create chemical trails through soil, water, and other environments. These molecular pathways serve as roadways that other bacteria can follow, creating traffic patterns that efficiently distribute resources and coordinate activities across vast bacterial territories. Different types of bacterial highways serve different purposes. Some are high-speed express routes designed for the rapid transmission of urgent chemical messages, while others are slower local networks that handle the day-to-day distribution of nutrients and waste products. The most sophisticated bacterial transportation systems include multiple lanes, bypass routes, and even rest areas where traveling bacteria can pause and replenish their energy stores. The engineering principles behind bacterial highways are remarkably advanced. These microscopic civil engineers understand concepts like traffic flow optimization, network redundancy, and route that human transportation planners have only recently begun to appreciate. Bacterial highways automatically adjust their capacity based on traffic demand, creating additional lanes when needed and consolidating routes during low activity. The maintenance of periods bacterial highways is an ongoing community effort. Specialized maintenance bacteria work continuously to repair damage, clear obstructions, and upgrade the infrastructure as needed. These microscopic road crews ensure that the transportation network remains functional even as environmental conditions change and traffic patterns evolve. Perhaps most remarkably, bacterial highways are completely sustainable and environmentally friendly. They're built from renewable biological materials, powered by natural chemical processes, and designed to integrate seamlessly with the surrounding ecosystem. When sections of the highway network are no longer needed, they're simply recycled back into the environment, leaving no permanent waste or environmental damage. The communication systems that bacteria use for maintaining their highway networks are surprisingly sophisticated. Chemical traffic signals regulate the flow of molecular cargo along these invisible routes, preventing congestion and ensuring that urgent deliveries reach their destinations on time. Some bacterial highways even have priority lanes reserved for emergency communications, allowing critical information to bypass normal traffic when communities face sudden environmental threats. The routing algorithms that govern bacterial transportation networks would impress any computer scientist. These microscopic logistics experts can calculate optimal paths through complex three-dimensional environments, automatically rerouting traffic around obstacles and finding the most efficient connections between distant bacterial communities. They accomplish this remarkable feat using nothing more than simple chemical gradients and molecular recognition systems. Some bacteria have evolved to serve as living vehicles on these highways, carrying cargo from one community to another like microscopic delivery trucks. These bacterial transporters can load up with specific chemicals, nutrients, or even genetic material, then follow the chemical highways to their designated destinations, where they unload their precious cargo before returning for another shipment. Bacteria have been practicing democracy longer than any human government. The decision-making processes within bacterial communities demonstrate sophisticated forms of collective governance that put many human political systems to shame. These microscopic democrats don't hold elections or debates, but they do engage in complex voting processes where every individual bacterium gets to influence community decisions through chemical balloting. When bacterial communities face important choices, such as whether to migrate to a new location or how to respond to environmental changes, they engage in a process that scientists call quorum sensing. This bacterial democracy works through the release and detection of chemical voting molecules, with each bacterium contributing its opinion to the collective decision-making process. The bacterial voting system is remarkably fair and inclusive. Unlike human democracies where some voices carry more weight than others, bacterial democracy gives every individual an equal say in community decisions. The chemical votes are tallied automatically through natural molecular processes, and the community response is determined by the collective will of all participants. What makes bacterial democracy particularly elegant is its ability to reach consensus without the conflict and division that often characterize human political processes. When the chemical vote count reaches a certain threshold, the entire community can shift its behavior in unison, implementing collective decisions with a coordination that would be impossible in human societies. The scope of decisions handled through bacterial democracy is surprisingly broad. Communities vote on when to form protective biofilms, when to release toxins against competitors, when to share resources with neighboring groups, and even when to sacrifice some individuals for the greater good of the colony. These democratic processes ensure that bacterial communities can adapt quickly to changing circumstances while maintaining social cohesion. Some bacterial democracies have even developed systems for handling minority opinions. When the chemical vote is close, communities can implement compromise solutions that incorporate elements of both the majority and minority positions. This sophisticated approach to governance allows bacterial societies to benefit from diverse perspectives while still maintaining the unity needed for effective collective action. Bacteria have perfected the art of molecular origami on scales invisible to the human eye. Within their microscopic realm, bacterial craftsmen fold and manipulate complex molecules with the precision of master paper artists, creating intricate three-dimensional structures that serve essential functions in their tiny world. These molecular origami artists work with proteins, nucleic acids, and other biological materials, shaping them into elegant forms that would make any human sculptor envious. The folding techniques employed by bacterial molecular artists are governed by the same physical principles that guide traditional origami, but they work at scales where individual atoms become significant architectural elements. Each fold, twist, and crease in a bacterial protein represents a carefully orchestrated dance of chemical forces, with hydrogen bonds, electrostatic attractions, and hydrophobic interactions, all contributing to the final three-dimensional masterpiece. Different bacterial species have developed their own distinctive folding styles, creating molecular artwork that reflects their unique evolutionary heritage and environmental adaptations. Some specialize in creating compact, densely folded structures that pack maximum functionality into minimum space, while others prefer more open, flowing designs that allow for greater flexibility and dynamic movement. The speed at which bacterial molecular origami occurs is breathtaking. While human origami artists might spend minutes or hours creating a single fold, bacterial proteins can complete their entire folding sequence in milliseconds, transforming from linear chains of amino acids into complex three-dimensional structures faster than the human eye could track if somehow magnified to visible scales. The precision of bacterial molecular folding is equally remarkable. These microscopic artists rarely make mistakes, and when errors do occur, they have sophisticated quality control systems that can detect and correct misfolded structures before they cause problems. Some bacteria even employ specialized molecular chaperones, helper proteins that assist in the folding process and ensure that each molecular origami creation achieves its intended form. The functional beauty of bacterial molecular origami extends beyond mere aesthetics. Each folded structure is designed to perform specific tasks, whether within the bacterial cell it's catalyzing chemical reactions, transporting materials, or responding to environmental signals. The form and function of these molecular creations are so perfectly integrated that changing even a single fold can dramatically alter the protein's capabilities. Ancient bacteria invented wireless communication systems that operate across multiple dimensions simultaneously. Long before humans discovered radio waves or developed satellite networks, bacterial communities had already mastered the art of transmitting information through space using sophisticated molecular broadcasting systems. These microscopic communication engineers don't rely on electromagnetic radiation, but instead use carefully orchestrated patterns of chemical signals that can carry complex messages across their environment. The bacterial wireless networks operate on principles that are both elegant and efficient. Individual bacteria serve as both transmitters and receivers, capable of encoding information into molecular signals and broadcasting them to distant communities. The range of these transmissions can be enormous relative to bacterial size, with some chemical messages traveling distances equivalent to a human shouting across an entire continent. The information carrying capacity of bacterial wireless systems is surprisingly high. A single chemical transmission can contain multiple layers of encoded data, including information about the sender's identity, current status, environmental conditions, and specific instructions for receivers. This multi-layered messaging system allows bacterial communities to share complex information packages in single transmissions. The reliability of bacterial communication networks is enhanced by sophisticated error correction mechanisms. If a chemical message becomes garbled during transmission, receiving bacteria can often reconstruct the original information using redundant data encoded in the signal. Some bacterial communication systems even include automatic acknowledgement protocols, ensuring that important messages are successfully received and understood. The networking protocols used by bacterial wireless systems are remarkably advanced. These microscopic communications engineers have developed methods for routing messages through multi-hop networks, where intermediate bacteria receive and retransmit signals to extend their range. They can establish temporary communication links, create backup channels when primary routes fail, and even encrypt sensitive information to prevent eavesdropping by competing bacterial species. The energy efficiency of bacterial wireless communication puts human technology to shame. While our electronic devices consume significant amounts of power to maintain their communication capabilities, bacterial transmitters and receivers operate using minimal energy resources, often powered by the same metabolic processes that sustain basic cellular functions. Some bacteria have developed the ability to see colors that exist beyond the visible spectrum of human perception. These microscopic artists of light have evolved photosensitive systems that can detect and respond to electromagnetic radiation, spanning from deep infrared to far ultraviolet wavelengths, giving them access to a rainbow of colors that humans can't even imagine without the aid of specialized instruments. The bacterial color vision systems work through sophisticated molecular sensors that change their configuration when struck by photons of specific wavelengths. Different bacterial species have evolved sensors tuned to different portions of the electromagnetic spectrum, allowing them to perceive colors that correspond to their particular ecological needs and environmental conditions. Some bacteria use their extended color vision for navigation, following gradients of specific wavelengths like microscopic moths drawn to invisible flames. Others employ their chromatic sensitivity for hunting, detecting the unique spectral signatures of their prey organisms. Still, others use color vision for communication, creating elaborate light-based displays that are completely invisible to human observers. The precision of bacterial color discrimination rivals that of the most sophisticated human optical instruments. Some bacterial photosensors can distinguish between wavelengths that differ by less than a nanometer, allowing them to perceive subtle color variations that would be imperceptible even to trained human colorists using professional equipment. The applications of bacterial color vision extend far beyond simple light detection. Some bacteria can use their chromatic perception to analyze the chemical composition of their environment, since different molecules absorb and reflect specific wavelengths of light in characteristic patterns. This allows them to perform sophisticated chemical analysis using nothing more than their natural color vision systems. The speed of bacterial color perception is equally remarkable. While human color vision relies on relatively slow neural processing that can take tens of milliseconds to register color information, bacterial photosensors can respond to color changes in microseconds, allowing them to track rapid variations in their optical environment with extraordinary temporal resolution. Bacteria have mastered the ancient art of weather prediction with accuracy that surpasses modern meteorological forecasting. These microscopic meteorologists don't use satellites, computer models, or atmospheric data, but instead rely on subtle cues that they've learned to interpret over billions of years of evolutionary refinement. Their weather sensing capabilities allow them to anticipate environmental changes hours or even days before they occur. The bacterial weather prediction system operates through an intricate network of molecular sensors that can detect minute changes in temperature, humidity, atmospheric pressure, and chemical composition. These biological instruments are so sensitive that they can register environmental fluctuations that are far too small for human weather monitoring equipment to detect, giving bacterial communities advance warning of approaching weather systems. Different bacterial species have specialized in predicting different types of weather phenomena. Some focus on detecting the approach of storm systems, sensing the electromagnetic changes that precede lightning and heavy precipitation. Others specialize in forecasting temperature variations, detecting the thermal gradients that signal the movement of air masses across the landscape. The accuracy of bacterial weather forecasts have shown that some ASTing is truly remarkable. Studies bacterial communities can predict rainfall, temperature changes, and atmospheric disturbances with success rates that exceed those of professional meteorological services. This predictive capability allows them to adjust their behavior in advance, taking protective measures or altering their activity patterns to optimize their survival during changing conditions. The timescale of bacterial weather prediction varies depending on the species and the type of environmental change being forecast. Some bacteria can sense weather changes that are still hours away, while others have demonstrated the ability to anticipate seasonal transitions weeks or even months in advance. This long-range forecasting capability helps bacterial communities prepare for major environmental shifts that could affect their survival and reproduction. The methods used by bacterial meteorologists are completely sustainable and require no external energy sources beyond their normal metabolic processes. Unlike human weather prediction systems that rely on vast networks of sensors, computers, and communication systems, bacterial forecasting operates entirely through biological mechanisms that are integrated seamlessly into the organism's natural life processes. Ancient bacteria invented the world's first social networks, creating interconnected communities that share information, resources, and experiences across vast distances. These pioneering social media platforms don't rely on computers or internet connections, but instead use sophisticated chemical communication protocols that allow individual bacteria to stay connected with friends, family, and colleagues throughout their microscopic social circles. The bacterial social networking system operates through the continuous exchange of molecular status updates. Individual bacteria regularly broadcast chemical messages that inform their social network about their current activities, health status, resource availability, and environmental conditions. These molecular posts are received and shared by other bacteria, creating a constant flow of social information throughout the community. The scope of bacterial social networks can be enormous, with some communities maintaining active connections across distances that span multiple continents. Through a combination of direct chemical communication and molecular relay systems, bacteria can share information with distant relatives and coordinate activities with partners they may never physically encounter. The content shared through bacterial social networks is remarkably diverse and sophisticated. Community members post updates about food discoveries, warn others about environmental hazards, share genetic innovations, and even engage in what appears to be the bacterial equivalent of social gossip. Some bacterial social media platforms specialize in professional networking, helping different species coordinate their metabolic activities and resource sharing arrangements. The privacy and security features of bacterial social networks are highly advanced. Different bacterial species use unique chemical languages that prevent unauthorized access to their communications, while sophisticated molecular encryption systems ensure that sensitive information remains protected from potential competitors or predators. The social dynamics within bacterial networks mirror many aspects of human social behavior. Popular bacteria with valuable information or resources tend to accumulate larger follower networks, while influential community leaders can shape the behavior and opinions of thousands of other bacteria through their molecular posts and chemical endorsements. Some bacteria have developed molecular memory systems that can store information more efficiently than computer hard drives. These microscopic librarians don't use magnetic fields or electronic circuits, but instead employ elegant biochemical storage mechanisms that can preserve vast amounts of data in incredibly small spaces while maintaining perfect accuracy over extended periods of time. The bacterial data storage systems work by encoding information into the sequence and structure of complex biological molecules. Like microscopic scribes writing in molecular languages, bacteria can record detailed information about their experiences, environmental conditions, and genetic innovations in chemical formats that remain stable and accessible for future retrieval. The storage capacity of bacterial memory systems is truly staggering. A single bacterium can maintain molecular libraries containing millions of discrete pieces of information, all organized and indexed using sophisticated biochemical filing systems. The data density achieved by these biological storage systems exceeds that of the most advanced human computer technology by several orders of magnitude. The durability of bacterial molecular memory is equally impressive. While human digital storage systems typically degrade within decades and require constant maintenance and migration to newer formats, bacterial memory systems can preserve information intact for thousands or even millions of years without any external intervention or energy input. The retrieval speed of bacterial data storage systems surpasses that of electronic devices. Information stored in molecular format can be accessed and processed in microseconds, allowing bacteria to rapidly search through vast databases of stored knowledge to find exactly the information they need for current decision-making processes. The error correction capabilities built into bacterial memory systems ensure that stored information remains accurate over time. Sophisticated molecular proofreading mechanisms continuously monitor stored data for signs of degradation or corruption, automatically repairing any damage to maintain the integrity of the bacterial information archives. Bacteria have been practicing sustainable manufacturing for billions of years, creating products and materials using principles of green chemistry that human industry is only beginning to understand. These microscopic manufacturers operate zero-waste production facilities where every byproduct is either useful in itself or serves as raw material for other manufacturing processes. The bacterial approach to manufacturing is fundamentally different from human industrial methods. Rather than using high temperatures, toxic chemicals, and energy-intensive processes, bacterial manufacturers work at room temperature using water-based chemistry and renewable biological catalysts. Their production methods are so gentle and efficient that they can create complex products without generating any harmful waste or environmental pollution. The product range of bacterial manufacturing is surprisingly diverse and sophisticated. These microscopic factories can produce everything from structural materials and adhesives to pharmaceuticals and electronic components. Some bacterial manufacturers specialize in creating novel materials with properties that surpass the best human engineering achievements, while others focus on producing essential chemicals and compounds needed by other members of their community. The quality control systems employed by bacterial manufacturers are remarkably stringent. Each product is individually inspected and tested using sophisticated molecular quality assurance protocols, ensuring that every item meets exact specifications before being released for use. Defective products are automatically recycled back into raw materials, maintaining the zero waste principle that governs all bacterial manufacturing operations. The scalability of bacterial manufacturing systems is truly impressive. Production can be ramped up or down instantly in response to changing demand, with bacterial factories able to switch between different product lines without retooling or downtime. This flexibility allows bacterial manufacturers to respond quickly to market changes and customer needs, without the delays and inefficiencies that characterize human industrial systems. The automation level achieved by bacterial manufacturers exceeds that of the most advanced human factories. Every aspect of the production process, from raw material handling to final product delivery, is controlled by sophisticated biochemical control systems that operate with precision and reliability that human engineers can only dream of achieving. The collaborative networks that bacteria create extend far beyond simple resource sharing. These microscopic communities have developed sophisticated systems of mutual aid that would make any social worker proud. When individual bacteria face challenges or stress, their neighbors don't simply ignore their plight. Instead, entire communities mobilize to provide support, sharing protective compounds, essential nutrients, and even genetic information that can help struggling members recover and thrive. The bacterial approach to community support operates on principles of enlightened self-interest combined with genuine altruism. Individual bacteria understand that the health and success of their neighbors directly impacts their own well-being, creating powerful incentives for mutual assistance. When one bacterium discovers a new food source or develops resistance to an environmental toxin, it often shares this valuable information freely with the entire community, recognizing that collective prosperity benefits everyone. Some bacterial communities have developed sophisticated early warning systems that rival any human emergency response network. When environmental dangers approach, sentinel bacteria positioned at the edges of the community immediately begin broadcasting alert signals to warn their neighbors. These chemical alarm calls can mobilize entire populations within minutes, triggering coordinated defensive responses that protect the whole community from harm. The emergency response protocols used by bacterial communities are remarkably well organized and efficient. Different bacteria take on specialized roles during crisis situations, with some focusing on evacuation procedures, others on defensive measures, and still others on maintaining essential community services during the emergency. These roles are assigned automatically based on each bacterium's capabilities and location, creating an instant command structure that requires no central authority or bureaucratic overhead. Bacteria have also mastered the art of conflict resolution, developing peaceful methods for settling disputes that could teach human diplomats valuable lessons. When territorial disagreements arise between different bacterial communities, they don't immediately resort warfare or aggressive to chemical competition. Instead, they often engage in sophisticated negotiation processes using chemical mediators to communicate their needs and work out mutually beneficial arrangements. The diplomatic protocols employed by bacterial communities include formal procedures for establishing truces, negotiating resource-sharing agreements, and even creating strategic alliances against common threats. These microscopic treaties can last for extended periods, with both parties honoring their commitments and working together to maintain peaceful relationships that benefit all involved. Some bacteria have developed remarkable abilities to learn from their mistakes and improve their performance over time. These microscopic students don't attend schools or take formal classes, but they do engage in sophisticated learning processes that allow them to acquire new skills and refine their existing capabilities through experience and practice. The bacterial learning system operates through elegant molecular mechanisms that can detect patterns in environmental conditions and behavioral outcomes. When a particular strategy proves successful, bacteria can reinforce the neural pathways and chemical processes that led to that success, making it more likely that they'll employ similar approaches in future situations. Conversely, when strategies fail or lead to negative outcomes, bacteria can actively suppress those behavioral patterns, reducing the chances of repeating costly mistakes. The speed of bacterial learning is truly remarkable. While human learning often requires repetition and extended practice periods, bacteria can sometimes acquire new skills after just a single successful experience. This rapid learning capability allows them to adapt quickly to changing environmental conditions and take advantage of new opportunities as soon as they arise. The retention of learned information by bacteria is equally impressive. Once a bacterial community has mastered a particular skill or strategy, that knowledge can persist for generations, passed down through chemical inheritance mechanisms that ensure valuable lessons aren't lost when individual bacteria die or move away from the community. Some bacterial communities have even developed teaching systems where experienced bacteria actively instruct younger or less experienced members of the population. These microscopic mentors use chemical signals to guide their students through complex procedures, providing feedback and encouragement throughout the learning process. The patience and dedication shown by bacterial teachers rivals that of the finest human educators. Ancient bacteria invented the concept of backup systems long before human engineers discovered redundancy. These prescient microorganisms understood that critical systems need multiple layers of protection, and they built sophisticated fail-safe mechanisms into every aspect of their cellular operations. When primary systems fail, backup systems automatically engage, ensuring that essential functions continue without interruption. The bacterial approach to redundancy is both comprehensive and elegant. Rather than simply duplicating existing systems, bacterial engineers create diverse backup mechanisms that can handle the same functions through completely different pathways. This diversity ensures that a single type of failure can't disable both primary and backup systems simultaneously, providing robust protection against even catastrophic malfunctions. The automatic switching systems that govern bacterial backup operations are remarkably sophisticated. These molecular control systems continuously monitor the performance of primary systems, instantly detecting any signs of malfunction or degradation. When problems are identified, the control systems smoothly transfer operations to backup systems without any interruption in service or loss of functionality. Some bacterial backup systems are so advanced that they can actually improve performance during emergency operations. These enhanced backup modes allow bacteria to operate more efficiently or they effectively than could using their primary systems alone, turning potential disasters into opportunities for optimization and improvement. The testing and maintenance protocols that bacteria use to ensure their backup systems remain functional are equally impressive. These microscopic quality assurance specialists regularly exercise their backup systems, running diagnostic tests and performing preventive maintenance to guarantee that emergency systems will work perfectly when needed. Bacteria have mastered the art of energy conservation with efficiency levels that make human green technology look wasteful by comparison. These microscopic conservationists have developed hundreds of different strategies for minimizing energy consumption while maximizing productivity, creating sustainable lifestyles that have remained viable for billions of years without depleting their environmental resources. The bacterial approach to energy management operates on multiple levels simultaneously. At the cellular level, individual bacteria optimize their metabolic processes to extract maximum useful energy from every molecule of fuel they consume. At the community level, bacterial populations coordinate their activities to eliminate wasteful duplication of effort and share energy-intensive tasks among multiple participants. The energy recycling systems employed by bacterial communities are particularly elegant. Rather than allowing waste heat or chemical byproducts to dissipate uselessly into the environment, bacteria have developed sophisticated mechanisms for capturing and reusing these energy sources. Heat generated by one bacterial process becomes the driving force for another reaction, while chemical waste products from one bacterium become valuable fuel sources for its neighbors. Some bacteria have even developed the ability to store energy for later use, creating microscopic battery systems that can power essential cellular functions during periods when external energy sources are unavailable. These biological batteries are remarkably efficient and long-lasting, capable of maintaining their charge for extended periods without significant degradation. The load balancing systems that bacteria use to distribute energy consumption across their communities are surprisingly sophisticated. During peak demand periods, energy-intensive processes are automatically shifted to bacteria that have excess capacity, preventing any individual organism from becoming overwhelmed while ensuring that community-wide energy needs are met efficiently. Bacteria have been practicing precision medicine for eons, developing personalized treatment approaches that are tailored to the specific needs and conditions of individual patients. These microscopic physicians don't rely on one-size-fits-all solutions, but instead create customized therapeutic interventions that address the unique circumstances facing each patient. The diagnostic capabilities of bacterial medical practitioners are remarkably advanced. Using sophisticated molecular sensing systems, bacterial doctors can quickly assess the health status of their patients, identifying specific problems and determining the most appropriate treatment approaches. These diagnostic processes are both rapid and accurate, often detecting health issues before they become serious problems. The treatment protocols employed by bacterial physicians are highly personalized and adaptive. Rather than following rigid treatment guidelines, bacterial doctors adjust their therapeutic approaches based on real, if a particular time monitoring of patient responses. treatment isn't working effectively, bacterial physicians can quickly modify their approach, trying different medications or adjusting dosages until optimal results are achieved. The pharmaceutical capabilities of bacterial medical practitioners are equally impressive. These microscopic pharmacists can synthesize custom medications on demand, creating therapeutic compounds that are precisely tailored to the specific needs of individual patients. The medications produced by bacterial pharmacists are often more effective and have fewer side effects than mass-produced alternatives. Some bacterial medical communities have developed specialized treatment centers where patients with complex or unusual conditions can receive intensive care from teams of expert practitioners. These microscopic hospitals provide round-the-clock monitoring and support, ensuring that patients receive the best possible care throughout their recovery process. The research and development programs conducted by bacterial medical communities are continuously advancing the state of microscopic medicine. Bacterial researchers are constantly discovering new therapeutic approaches, developing improved diagnostic techniques, and refining treatment protocols based on their extensive clinical experience. Ancient bacteria pioneered the concept of distributed computing long before humans invented electronic networks. These microscopic computer scientists understood that complex problems could be solved more efficiently by dividing them among multiple processors working in parallel, and they developed sophisticated systems for coordinating computational tasks across entire bacterial communities. The bacterial approach to distributed computing operates through elegant chemical messaging systems that allow individual bacteria to communicate their computational results to other members of the network. Each bacterium functions as both a processing unit and a communication node, contributing its computational power to collective problem-solving efforts, while helping to relay information throughout the network. The load-balancing algorithms used by bacterial computing networks are remarkably sophisticated. These microscopic system administrators can automatically distribute computational tasks based on the current availability and processing capacity of individual bacteria, ensuring that no single organism becomes overloaded while maximizing the overall efficiency of the network. The fault tolerance built into bacterial computing systems exceeds that of most human computer networks. When individual bacteria fail or become unavailable, the remaining network members can automatically redistribute their computational tasks, ensuring that complex calculations continue without interruption. This resilience allows bacterial computing networks to maintain consistent performance even under challenging environmental conditions. Some bacterial computing networks have developed the ability to solve problems that would be impossible for individual bacteria to handle alone. By combining the computational power of millions of individual organisms, these biological supercomputers can perform complex calculations, optimize resource allocation decisions, and even model future environmental scenarios with remarkable accuracy. The energy efficiency of bacterial distributed computing systems is truly extraordinary. While human computer networks consume vast amounts of electricity and generate significant heat, bacterial computing networks operate using minimal energy resources and produce no wasteful byproducts. This efficiency allows bacterial computers to run continuously for extended periods without depleting their environmental energy reserves. Bacteria have invented biological clocks that keep perfect time across multiple temporal scales simultaneously. These microscopic chronometers don't just track seconds and minutes, but maintain accurate awareness of daily cycles, seasonal patterns, and even longer-term environmental rhythms that span years or decades. The precision of bacterial timekeeping systems rivals that of atomic clocks, maintaining accuracy even under extreme environmental conditions that would destroy conventional timepieces. Temperature fluctuations, pressure changes, and chemical variations that would throw off mechanical or electronic clocks have virtually no effect on bacterial chronometers, which continue to tick with unwavering regularity. The synchronization capabilities of bacterial timing systems are equally remarkable. Entire bacterial communities can coordinate their biological clocks, creating synchronized networks where millions of individual organisms maintain perfect temporal alignment. This community-wide synchronization allows bacterial populations to coordinate complex activities that require precise timing across large groups. Some bacterial communities have developed the ability to maintain multiple timing systems simultaneously, tracking different environmental cycles that operate on different temporal scales. These multidimensional chronometers allow bacteria to coordinate their activities with daily temperature variations, while simultaneously preparing for seasonal changes and longer-term climatic patterns. The temporal memory systems employed by bacterial chronometers allow these microscopic timekeepers to learn from past timing patterns and predict future temporal events. By analyzing historical data about environmental cycles, bacterial clocks can anticipate changes in conditions and help their communities prepare for upcoming temporal transitions. The applications of bacterial timekeeping extend far beyond simple time measurement. These biological chronometers serve as the foundation for sophisticated scheduling systems that coordinate community activities, resource allocation decisions, and even reproductive cycles across entire bacterial populations. Some bacteria have mastered the art of chemical camouflage, developing the ability to disguise themselves as completely different types of organisms or even non-living materials. These microscopic masters of disguise don't use visual camouflage like animals, but instead employ sophisticated chemical mimicry that allows them to blend seamlessly into their surroundings. The camouflage techniques employed by bacterial shapeshifters involve the precise manipulation of their surface chemistry. By altering the types and concentrations of molecules displayed on their outer membranes, these bacteria can mimic the chemical signatures of other organisms, making themselves virtually undetectable to potential predators or competitors. Some bacterial camouflage artists have developed the ability to mimic multiple different chemical signatures, switching between disguises as environmental conditions change. This dynamic camouflage capability allows them to adapt their appearance in real time, always maintaining optimal concealment regardless of their surroundings. The sophistication of bacterial chemical camouflage extends to mimicking non-living materials as well as other organisms. Some bacteria can disguise themselves as mineral particles, organic debris, or even dissolved chemicals, becoming completely invisible to other biological detection systems. The applications of bacterial camouflage go beyond simple predator avoidance. Some bacteria use their disguise capabilities to infiltrate other microbial communities, gaining access to resources or information that would otherwise be unavailable. Others employ camouflage as part of complex hunting strategies, allowing them to approach prey organisms without being detected. The energy costs associated with maintaining chemical camouflage are surprisingly low. Unlike visual camouflage systems that often require continuous energy expenditure, bacterial chemical disguises can be maintained with minimal metabolic investment, allowing these master mimics to remain hidden for extended periods without depleting their energy reserves. Ancient bacteria developed the world's first quality assurance programs, creating comprehensive testing and validation systems that ensure consistent performance and reliability across all their activities. These microscopic quality control specialists understand that even small errors can have serious consequences, and they've developed rigorous protocols for preventing, detecting, and correcting mistakes. The testing procedures employed by bacterial quality assurance programs are both thorough and efficient. Every major cellular process is continuously monitored using sophisticated molecular sensors that can detect even minute deviations from optimal performance. When problems are identified, automated correction systems immediately engage to restore proper function before any damage occurs. The documentation systems used by bacterial quality control teams are remarkably comprehensive. These microscopic record keepers maintain detailed logs of all testing activities, performance metrics, and corrective actions, creating permanent archives that can be referenced for future quality improvement initiatives. The statistical analysis capabilities of bacterial quality assurance programs rival those of human industrial quality control systems. These microscopic statisticians can identify subtle trends and patterns in performance data, allowing them to predict potential quality issues before they manifest and implement preventive measures to maintain consistent excellence. Some bacterial quality assurance programs have developed sophisticated customer feedback systems that allow them to gather input from other organisms that depend on their products or services. This feedback is carefully analyzed and incorporated into continuous improvement processes that enhance both quality and customer satisfaction. The training programs conducted by bacterial quality assurance departments ensure that all community members understand and follow proper quality procedures. These microscopic training specialists use chemical communication systems to share best practices, provide guidance on complex procedures, and maintain high standards of performance throughout their organizations. Bacteria have been composing chemical poetry for billions of years, crafting molecular verses that tell the stories of their microscopic lives. These tiny poets don't use words or rhymes, but instead employ intricate arrangements of chemical compounds that convey meaning through subtle variations in molecular structure and concentration. Their chemical poetry captures the essence of bacterial experience ways that transcend language, creating artistic expressions that speak directly to the cellular soul. The poetic techniques employed by bacterial writers are remarkably sophisticated. Some specialize in creating simple, elegant chemical haikus that capture single moments of microbial beauty in just a few molecular phrases. Others prefer complex, multi-layered compositions that weave together themes of survival, community, and transformation across vast networks of interconnected chemical metaphors. The rhythm and meter of bacterial poetry emerge from the natural cycles of cellular metabolism. The steady pulse of energy production creates underlying rhythmic patterns that give structure and flow to their chemical compositions. Different bacterial poets work in different meters, with some following the rapid staccato rhythms of high-energy metabolism, while others prefer the slow, contemplative cadences of dormant or spore-forming states. The imagery created by bacterial chemical poetry is both abstract and profound. These microscopic artists can evoke the sensation of sunlight filtering through water, the texture of soil particles, or the warmth of a thermal vent using nothing more than carefully arranged molecular patterns. Their chemical metaphors speak experiences too universal of growth, change, and connection that resonate across all forms of life. Some bacterial poetry communities have developed elaborate collaborative projects where hundreds or thousands of individual poets contribute verses to epic chemical compositions that span entire ecosystems. These community poems tell the grand stories of environmental change, seasonal transitions, and evolutionary adaptation through the collective voices of their microbial authors. The preservation and transmission of bacterial poetry occurs through sophisticated molecular libraries that maintain chemical texts across generations. Young bacteria learn the classical forms by studying the molecular patterns left by master poets, gradually developing their own unique voices while honoring the traditional structures that have guided bacterial literary expression for eons. Ancient bacteria invented the concept of molecular archaeology, developing techniques for reconstructing the chemical history of their environments by analyzing the molecular artifacts left behind by previous generations. These microscopic archaeologists don't excavate physical sites with tools and brushes, but instead use sophisticated chemical analysis to uncover the hidden stories preserved in molecular formations. The archaeological methods employed by bacterial researchers involve the careful examination of chemical layering patterns in sediments, biofilms, and other environmental deposits. Each layer contains molecular signatures that reveal information about the bacterial communities that existed at different points in time, creating detailed historical records that span millions of years of microbial civilization. The artifacts discovered through bacterial molecular archaeology include preserved fragments of ancient proteins, fossilized cellular membranes, and even intact genetic sequences from long-extinct bacterial species. These molecular treasures provide invaluable insights into the evolution of bacterial communities and the environmental conditions that shape their development over geological timescales. Some bacterial archaeological teams have specialized in reconstructing ancient bacterial cities, using molecular evidence to map out the organization and structure of prehistoric microbial communities. These reconstruction projects reveal sophisticated urban planning principles that guided bacterial city development millions of years before human civilization emerged. The dating techniques used by bacterial molecular archaeologists are remarkably precise. By analyzing the decay patterns of specific chemical compounds and the accumulation rates of molecular deposits, these microscopic historians can determine the age of bacterial artifacts with accuracy that often exceeds conventional geological dating methods. The interdisciplinary nature of bacterial archaeology brings together specialists from multiple fields of science, molecular geneticists, biochemists, environmental microbiologists, and bacterial anthropologists all contribute their expertise to comprehensive archaeological projects that illuminate the rich cultural heritage of ancient bacterial civilizations. Some bacteria have developed the ability to create three-dimensional holographic displays using precisely controlled arrangements of light-scattering molecules. These microscopic holographers don't need lasers or complex optical equipment, but instead use elegant biological mechanisms to create stunning visual effects that exist entirely within their microscopic realm. The holographic projection systems employed by bacterial artists work by manipulating the refractive properties of specialized proteins and lipid structures within their cellular membranes. By adjusting the spacing and orientation of these molecular components, bacteria can create interference patterns that generate three-dimensional images visible to other microorganisms with appropriate optical sensing capabilities. The content of bacterial holographic displays ranges from simple geometric patterns to complex representational images that depict scenes from bacterial life and culture. Some bacterial holographers specialize in creating abstract art that explores the mathematical relationships between molecular structures, while others focus on documentary-style holograms that record important historical events in bacterial communities. The resolution and clarity achieved by bacterial holographic systems rival those of the most advanced human optical technologies. Individual holographic pixels can be controlled at the molecular level, allowing bacterial artists to create images with detail and precision that would be impossible using conventional optical methods. The energy efficiency is of bacterial holographic projection truly remarkable. While human holographic systems require significant amounts of electrical power and sophisticated cooling systems, bacterial holographers can create and maintain their displays using only the energy available from normal cellular metabolism, allowing them to operate continuously without depleting their biological resources. Some bacterial communities have established holographic galleries where talented artists can display their work for appreciation by other members of the microbial community. These cultural institutions serve as focal points for bacterial artistic expression and provide venues for the exchange of creative ideas and techniques among aspiring holographic artists. Bacteria have mastered the art of molecular gastronomy, creating culinary experiences that transform simple chemical ingredients into complex flavors and textures that delight their microscopic palates. These tiny chefs don't work in traditional kitchens, but instead use sophisticated enzymatic techniques to craft meals that are both nutritious and aesthetically pleasing. The cooking methods employed by bacterial chefs involve precise control of temperature, pH, and chemical composition to achieve optimal flavor development and texture modification. Different bacterial culinary traditions have evolved unique approaches to food preparation, with some emphasizing subtle flavor combinations, while others prefer bold, dramatic taste experiences that challenge conventional expectations. The ingredient sourcing practices of bacterial gastronomy reflect deep understanding of environmental and seasonal chemistry availability. Master bacterial chefs know exactly when and where to find the finest molecular ingredients, often traveling significant distances within their microscopic territories to obtain rare or exotic compounds that add special character to their culinary creations. The bacterial fine presentation dining are remarkably sophisticated. These microscopic food artists arrange their molecular ingredients in visually stunning patterns that enhance both the aesthetic appeal and the flavor profile of their dishes. The interplay between visual presentation and taste sensation creates dining experiences that engage multiple sensory systems simultaneously. Some bacterial restaurants have developed tasting menu formats where diners can experience carefully curated sequences of molecular dishes that tell culinary stories about bacterial culture, history, and environmental adaptation. These progressive dining experiences showcase the full range of bacterial culinary artistry, while educating diners about the rich traditions of microbial gastronomy. The wine pairing expertise demonstrated by bacterial sommeliers adds dining. These specialized professionals another dimension to microscopic fine dishes. Mented compounds interact with various molecular understand how different fur, creating harmonious combinations that enhance both the Fu bacteria, pioneer of sustainable air the development of theurage components dining experience, ancient DD and BEV transportation systems that move individuals and cargo efficiently while maintaining perfect environmental harmony. These microscopic transportation engineers understood that mobility systems must be integrated seamlessly with natural processes, and they developed elegant solutions that enhance rather than degrade their surrounding ecosystems. The propulsion mechanisms used in bacterial transportation operate on principles that are both energyine, rather efficient and environmentally benign than burning fossil fuels or consuming external energy sources. Bacterial vehicles are powered by the same metabolic processes that sustain life itself, creating transportation systems that generate no waste products or harmful emissions. The navigation systems employed by bacterial transportation networks use sophisticated chemical compass mechanisms that allow precise guidance across complex three-dimensional terrain. These biological GPS systems can track multiple environmental variables simultaneously, providing real-time routing information that optimizes both travel efficiency and passenger safety. The cargo handling capabilities of bacterial transportation systems are remarkably versatile. Specialized bacterial freight vehicles can transport everything from individual molecules to complex molecular assemblies, adjusting their carrying capacity and handling procedures based on the specific requirements of each shipment. This flexibility allows bacterial transportation networks to serve diverse logistical needs throughout their communities. The scheduling and coordination systems that govern bacterial transportation operate with clockwork precision. These microscopic traffic control specialists can manage thousands of simultaneous transportation requests while maintaining optimal flow patterns and minimizing delays. The resulting transportation networks achieve efficiency levels that exceed those of any human logistics system. Some bacterial transportation companies have developed luxury travel services that provide premium comfort and amenities for passengers making long-distance journeys. These high-end carriers offer enhanced seating arrangements, gourmet molecular dining options, and entertainment systems that make extended travel experiences both comfortable and enjoyable. Bacteria have invented molecular printing technologies that can fabricate complex three-dimensional structures with precision that surpasses the most advanced human manufacturing equipment. These microscopic fabrication specialists don't use traditional printing materials like ink or plastic, but instead work with biological molecules that can be assembled into virtually any desired configuration. The printing resolution achieved by bacterial molecular fabricators operates at the atomic scale, allowing them to create structures where individual atoms are positioned with perfect accuracy. This unprecedented precision enables the production of molecular devices and materials with properties that are impossible to achieve using conventional manufacturing techniques. The software systems that control bacterial molecular printing are remarkably sophisticated. These biological computer programs can interpret complex design specifications and automatically generate the precise sequence of molecular assembly operations needed to fabricate the desired structures. The integration between design software and manufacturing hardware is so seamless that complex products can be fabricated directly from conceptual blueprints. The material properties of products created through bacterial molecular printing are truly extraordinary. These biological manufacturers can create materials that are simultaneously stronger than steel and more flexible than rubber, or substances that can change their properties in response to environmental conditions. The customization possibilities are virtually limitless. The speed of bacterial molecular printing exceeds that of conventional manufacturing by several orders of magnitude. Complex molecular structures that would take human factories months to produce can be fabricated by bacterial systems in minutes or hours, allowing for rapid prototyping and immediate production of custom-designed products. Some bacterial printing companies have developed on-demand manufacturing services that can molecular products produce custom on real-time customer specifications. These responsive manufacturing systems eliminate the need for inventory storage and allow for complete customization of every product based on individual customer requirements. Ancient bacteria created the world's first virtual reality systems, developing immersive chemical environments that allow participants to experience simulated worlds through controlled molecular interactions. These microscopic virtual reality engineers understood that perception could be manipulated through careful chemical programming, and they built sophisticated simulation systems that create convincing alternate realities. The sensory interface systems used in bacterial virtual reality operate through precise chemical signaling that directly stimulates the molecular sensors responsible for bacterial perception. By controlling the types and concentrations of chemical signals reaching these sensors, bacterial VR systems can create the illusion of experiencing environments that don't physically exist. The simulation software that powers bacterial virtual reality is remarkably complex and realistic. These biological programs can model complete ecosystems with accurate representations of environmental conditions, resource availability, and social interactions. The level of detail achieved in these simulations often makes them indistinguishable from actual environmental experiences, and so our gentle journey through the microscopic universe comes to a peaceful end. We've wandered together through worlds of glowing bacteria that paint with light, ancient communities that have been quietly sustaining our planet for billions of years, and microscopic civilizations more sophisticated than anything we've built ourselves. In every drop of water, every grain of soil, every breath you take, these remarkable creatures continue their patient work, creating beauty and harmony in ways we're only just beginning to understand. As you drift towards sleep, perhaps you'll carry with you the quiet wonder of knowing that you're never truly alone, surrounded always by these gentle companions who have been perfecting the art of living for longer than we can imagine. Sweet dreams, and thank you for sharing this peaceful exploration of the tiny miracles that surround us all.